My name is Alan Burden. I'm a postdoc research fellow in Program 3 of the Australian Cobotics Centre, and along with my co-leaders, Associate Professor Glenda Caldwell and Dr. Matthias Gertler, we do research into socio-technical systems, looking at approaches to designing collaborative robotics for the manufacturing industry. So socio-technical systems, we're looking at the social and the technical aspect, along with the technology and the materials that are being used. And those are all looked at as independent parts of a bigger, more complex system. And generally, we ask the question, how can we design these for more complex systems? So today I'm going to talk about digital twins and some of the immersive technologies that can give us new opportunities for our design and evaluation through research. Sorry, slight delay there. Okay, a little bit about me. That's me in the photo. I'm originally from a very pretty part of the UK called Surrey, which is just outside of London. My accent betrays me sometimes. I've spent most of my life in Australia, and most of my formal education has been here in Queensland. Straight out of school, I studied science and worked in diagnostic healthcare for well over a decade before I returned to my early creative passion, which was design and digital fabrication, and I went through and earned my master's in architecture. I worked for a few years in some Brisbane and overseas architecture studios before being given an opportunity to do some research in what I became quite interested in at that time, building information modeling and digital architecture here at QUT. So from information modeling at QUT, I moved into another research group doing something similar, 3D environments and visualization. That's where I first had an interest in scanning, and that role gradually changed from data analysis and modeling into what was my first taste of user experience design and interaction design. And that led me to another opportunity to apply for a scholarship with the QUT Design Robotics Group, where I looked at creative outcomes of design in bespoke manufacturing. And all this has led to my current role in researching human-robotic collaboration as a postdoc. So this is a map of today's presentation. I'll talk a little bit about digital twins, and I'll look at a few of the definitions and the subtypes that are being used. I'll show just a few examples from industry, and also look at two Cobotic research studies that have demonstrated the use of both digital twins, but also immersive environments, and specifically AR and VR. Then we'll take a look at immersive technology devices and the current classifications of reality technologies. And in the time that we have, I'll highlight just three of the devices, which are the HoloLens 2, the Quest 2, and the recently released Quest Pro. I'll outline some of the functionality of each, and also the general workflow in creating an application that can go into XR, extended reality tech. And then finally, I'll talk about our work in progress for Program 3, which is our research translation project with our brilliant industry partner, B&R Enclosures, where we are creating a VR platform for future research. And I'll look at the methods that we use to study the workers and also to capture the scans of that workplace. So what exactly is a digital twin, and why should you care about that? In the simplest definition of the concept, a digital twin is a virtual or a non-physical model that's designed to accurately reflect a physical model. However, it gets very complicated because in many different industries, a digital twin is also a virtual representation of an object or a system that can span the full life cycle of that object, and is normally updated from real-time data, and can also use simulation or machine learning or complex reasoning to help decision making. Within the automotive industry, as one example, it's defined normally as a digital non-physical model that's designed to accurately reflect physical or artificial systems, and it uses sensors to acquire a variety of data which concerns that system as well. So generally, digital twins let us understand the present and predict the future, but in many cases, they're also capable of allowing us for predictions of future outcomes. It's worth noting that they're not just also a digital clone of a physical copy, although many of them are, many of the examples are. They can also be representative of something contained within a physical element. So for example, research on brain neural pathways might contain data about those pathway connections or the organization of brain data, but not the actual physical structure of the brain itself. So digital twins are characterized by three subsystems shown in this diagram, and they all work in a continuous cycle. You get the physical components in the orange side there, which shows physical real space, and that's where data acquisition occurs and happens normally through sensors. Then you get a digital equivalent in digital space, which is the green section, and that's where the data processing occurs. And then you get the intermediate layer where data and information ties the digital and the real together, known as communication and information sharing. Overall, the digital twin is ubiquitous with manufacturing and industry 4.0, but as more industries have digitized, the current trends are showing that they're going to be widespread in every aspect of our life, such as health and medicine. Many of us already wear smartwatches, which have sensors in them that can monitor heartbeat and blood oxygen levels. So it's not too far-fetched that we might actually have a personal digital twin in the future to predict our health. So because of the variations of definitions in different industry scenarios, there have been many classifications, but there are two models that have tended to prevail. The first, older model, puts digital twins into three stages. It creates a prototype, and this includes a design analysis, processes of the product, and which is simulated before there's an actual physical product. Then it creates instances. So the digital information is representing the life cycle of the product. And then eventually you have an aggregate, which is an aggregate of all the instances, and it shows the collective changes between the different versions of those instances. And is generally used for digital analysis and simulation and prediction. More recently, holistic models of digital twins have been proposed following the idea that there might be one digital representation that can perform all the tasks. And this follows a 3P approach. So you get a digital twin of the product, then you get a twin of the production of the product, and then you get a twin of the performance of the product. So, and this is already contained within one model. And this reflects on the advances to kind of the fundamental technologies that support twinning, which is sensor technology, so connection and gathering data, cloud computing, simulation and emulation, the Internet of Things, which is the general connectivity and networking of all devices to the internet, and then artificial intelligence as well. So a timeline gives a bit of an explanation for the diversity of digital twins. Historically, the origins begin in aerospace with the Apollo space program in 1970. I'm going to talk a little bit more about that in the next slide. There's conceptually, the idea came from science fiction in the 1990s, but it wasn't until 2002 that Michael Greaves, a professor at University of Michigan, came up with a concept for product lifecycle management. And it didn't really get used until NASA, who have been using what they refer to as virtual twinning since the Apollo space program, started to give it its first definition, and they were the ones attributed with really cementing the idea of a digital twin in 2010. In 2016, the concept became catalyzed and widespread because of many industries promoting Industry 4.0, and each sector was adopting their own definitions for their own use, hence the diversity of twins. So the historical digital twin example in aerospace is the Apollo 13 program, which is widely believed to be the first digital twin. This started off as simulators, so 15 simulators were used to train the astronauts and the mission controllers. It's shown there in the top left-hand corner. It's Ken Mattingly, who was one of the pilots from the later Apollo program. He didn't end up going on Apollo 13 because he had exposed to measles, and he ended up being the operator of the first digital twin here on Earth when famously the Apollo 13 lunar module had an explosion with the gas tanks traveling to the moon, and they had to bring them back to Earth safely. So the representation here is that the simulation on Earth was quickly converted into a digital twin. They adapted the simulator to match the conditions of the actual damaged spacecraft. And this was using high fidelity models, so trying to get as close to reality as possible to explore solutions and predict the results. In the bottom left of this slide, you can see an image with the two simulators. The mission control simulator is the tan colored one at the back. And that was used to kind of simulate everything that happened within mission control, including the data that they received. And the lunar module is the green simulator at the front there, which was the one that was considered the first digital twin. And that was the one that was used in order to create a device to remove the excess carbon dioxide that was filling up the lunar module. The center image there shows the device they created here on Earth inside the digital twin. And the image on the right shows the actual same module that they created to remove carbon dioxide in the Apollo 13 module in space at the time. This is a render from NVIDIA software, and this is a production factory concept in the collaboration between BMW, Siemens, and NVIDIA. It's run through NVIDIA Omniverse. NVIDIA spent a lot of money trying to make their Omniverse platform a new future standard for digital twinning and also for robotic control. In this factory, they're using prototypes and predictive algorithms to monitor and also plan and make the factory floor more efficient. And the digital people, it's worth noting, are for ergonomic and safety analysis. So they've actually mapped all the kind of movements that a person might have to do in a factory in order to create and build a car. And they're using this as a way to kind of limit the kind of unsafe postures that somebody might do and the gestures that they might have to undertake. Demonstration for NVIDIA is very much for them to stake a claim in digital technologies. They already are dominating part of the hardware scene with graphical chips. And this is their way of moving into robotics and to the future factories. Something should be said about HiTopo, which is a Chinese visualization company. They specialize in making human readable visualizations that are easily accessible through the web. So they specialize in digital twins, particularly that can just show real-time access to infrastructure within China. In the top left, we have an iron smelter, which is showing real-time delivery of supplies and supply levels and demands of the system at the time. In the top right, we have power station infrastructure shown through a web browser. And this shows real-life sensors being updated per the second and flagging any warnings. And in the bottom left, we have the wind turbine, which is showing maintenance schedules, critical data, real-time data, such as power produced, revolutions per minute of the propellers, and how much the network is producing at a given time. Formula One is widely considered to be one of the leaders in digital twin technology. This started about 40 years ago when McLaren started putting about 40 sensors on their first cars. Now the average Formula One car has about 300 sensors, and that produces approximately 1.1 million points of telemetry data between those variables. So that works out to being about 2 gigabytes of data per race lap. Those sensors fire at about 10,000 times per minute. Overall, the industry is very secretive about the advances it makes through digital twins and through sensor data and monitoring, because any advantage they have is an advantage over their competitor. So over a race weekend, terabytes of data is produced, that's analyzed, and typically every aspect of the car has a digital twin, including the tires and tire compounds. And this is used to feed into the following race weekend throughout the week, and then they produce a new car. So the cars are effectively mostly rebuilt from one race weekend to the next race weekend, all through digital twins and through simulations. It's typical that a lot of the Formula One and motorsport research and technology outcomes make their way down into the actual automotive industry. Most automotive industries will happily show you a very flash graphic about their digital twins, but they won't actually show you any information. Renault are one of the few which will actually show a few well curated slides. So we can have here at the bottom these two images. One is a crash simulation using a digital twin of a Renault car, and on the right hand side at the bottom is just showing some of the components in a digital twin of a Renault car as well. And it's not surprising that Renault actually does have a Formula One team that makes the engines and the body work as well. Dassault systems have been strongly associated with Renault Dassault, part of the aerospace company Airbus, which used to use digital twins and still do use digital twins to make their planes and for simulation data. So there's a strong connection between aerospace and automotive. These are two examples of research in Cobotics that also just happen to use immersive technologies, VR and AR. The first is from 2018. It's Malik and Bleiberg in Denmark, and they use AR to simulate, that's augmented reality, to simulate interactions between humans and robotics on an assembly line. And they do this to design and plan future collaboration tasks. It's very difficult to see in this slide, but they used an original HoloLens 1, which was quite a cumbersome device to use. But they used a lot of those metrics that were capable to measure human robot interaction, such as the movement of the human around that space, points of contact between the human and materials, and also the robot and materials as well. The second is a more recent study. It also provides a framework for safety and ergonomics. This is from Weistroffer and others, and uses VR marker trackers made by HTC Vive, who you might remember made mobile phones many years ago. And they use two types of tracking camera as well, the Zen camera for the environmental capture, and also a Microsoft Kinect Azure, which is one of the new versions of the Microsoft Kinect cameras to track people's movements within that space. So this is basically capturing people's body metrics. The goal of this project was to help people evaluate the posture, safety, and the ergonomics of a human during an activity. So there's a visual outcome here that can be shown through either VR or AR. Visually, a poor posture is represented in that virtual representation of a human overlaid over the real person there. Green is a good posture location, and red is considered to be a poor posture and poor ergonomics in moving that heavy weight along the sliding counter. So with those two research projects, they demonstrated that reality technologies are commonplace within digital twins and are typically part of a bigger field that's called immersive environments. So currently these are generally referred to as XR, it's highly stylized. The X means a variable for whatever's going to happen into the future with reality technologies, but also generally it's referred to as extended reality. So all of these forms are referred to as extended reality, and that's now accepted as the umbrella terminology for all of these technologies. I'll explain each of these terms with a visual example in the next slide, but for now, XR basically contains two subtypes, virtual reality and then mixed reality. And then mixed reality itself is an overall terminology for what was commonly known as the blending between augmented reality and another terminology which is not very commonly used, augmented virtuality. This slide shows the full range of what used to be called the virtuality spectrum, which is now generally extended reality. The diagram shows that you get the full range of realities from the real world on the left-hand side, pure reality, which most of us are very used to. And then each stage towards the right will show more virtual elements. So you've got the first of the mixed realities, augmented reality, where you get virtual elements added to the real environment. Augmented virtuality, where you'll get real objects and real environments replaced with a representation of a virtual version, but you still have reality versions coming through. And then virtual reality itself, which is a complete alternate reality. So you have a completely blinkered view where the complete environment and also the objects to interact with are all virtually created, and you can view them. This is one of three devices that we'll look at. It's important to note that there are different types of reality technology. You can also get things such as cave systems, which is like a projected suite that surrounds you. So as you walk around the space itself, you get a representation of what it is to be in a different environment. The augmented reality headsets are typically a very good way to kind of map your environment and to display it in a personal level and incorporate your personal movements. So this here is one of the better and probably considered to be the best in augmented reality for industry. This is a HoloLens 2, which is made by Microsoft. It's a continuation of the first HoloLens that they made and this provides a lot more functionality for industry, and such as having a tilting visor. The old one didn't have a tilting visor and was quite cumbersome to take on and off. This one has a tilting visor, is designed to be worn with an industrial hard hat, for example, and is generally geared for professional applications rather than for games. So the potential for this was also touted for the military, and the US military actually signed a very large contract with Microsoft to provide HoloLens for testing. And the idea was to relay data to soldiers on the actual battlefield in real time. The HoloLens contains a computer at the back, and the chunky bit that's at the back of the head there. It's surprisingly well balanced because of that, but does get quite warm, particularly if you're in a factory environment. It is remarkably comfortable though. I wore one of these for a large portion at the end of my PhD, and you'd often forget that you actually were wearing one. And as you can see, you can also wear it with corrective lenses with glasses as well. The HoloLens can independently run its own software on that computer that's inbuilt, or you can stream data from another computer to the display via Wi-Fi. There's no tethered wired connection with the HoloLens. The wires are just purely for recharging the battery. And it works by projecting an image onto a set of prism lenses on the inside of the visor, which is quite inobtrusive. And it has two speakers built into the left and right of the headband, so you can get stereoscopic sound as well. The cameras on the outside edge of the visor scan the outside environment, and they map the space entirely, which can then be used in the application as incoming data. This is what you can see through the HoloLens as an example. So you can see in the left-hand side, the person's actual environment, their chair, their sideboard, and then you can place elements over the top of it, such as a piano. This uses hand tracking, which the hand tracking has got a slight lag to it, but the functionality is definitely geared towards interaction of tracking how people can touch and move items that are virtual. The showcase generally aims towards, as I said, industry rather than games. And I think this has been one of the pitfalls of the HoloLens. It hasn't been as popular as VR and other elements. HoloLens 3 has been put on a permanent hold. It doesn't look like we're likely to see it anytime soon. And this is largely contributed to the HoloLens costing a lot. It was about 3,000 to 4,000 Australian dollars, and even more for development kit, which was considered too expensive even for professional industry. This is a VR device, which is a head-mounted display, a Meta Quest 2. This is definitely the most popular one. I think it sold about almost 15 million units, and famously they sold them at a loss originally, which is probably why they're everywhere. The Oculus company was the catalyst for modern VR, and it used crowdfunding in their very first devices as a way to just bring the display output, which is normally used for a monitor, into an actual headset. The company was later bought on by Facebook and is now called Meta, and this is being used as a platform for launching its well-hyped metaverse. The Quest is one of the Quest 2, sorry, is one of the better interfaces, and it's been brought in. They spend a lot of money at Meta to reduce that barrier of entry for consumers. So it's something that's relatable and quite easy to use straight out of the box. Like most head-mounted devices for VR, it works by blinkering the user, providing a complete eye cover, and the display sits rather close in front of the eyes. The first devices were a little more, you probably remember the Samsung Gear. It was just a mobile phone that basically sat in front of your eyes. These ones are definitely geared using Fresnel lenses so that your eyes aren't straining definitely as much. The old ones, you could definitely feel your eyes straining and getting worse while you're wearing them. These ones are very comfortable, and the resolution with each version gets better and better. So it actually is feeling more natural and intuitive to be in VR. The Quest 2 comes with 2 hand controllers, and that provide the buttons for index fingers, such pointing an index finger or closing it in, gripping something as a grip button with the middle finger, and thumb joysticks as well to control movement. So you can stand still and use the thumbsticks to move around the space, or you can actually walk around the space if you have a big enough VR area as well. And they also provide haptic feedback through a kind of a knocking vibration as well on the controller. Similar to the HoloLens 2, the cameras on the Quest 2 scan the environment from the inside out. They use the 4 cameras on the edge of the visor, and they can scan the environment, map the real world, and then you can use that for virtualization as well within the app, and then gather that data. The device is wireless. A few people will remember the first VR headsets that came out, particularly the HTC Vive, which you can see in the top left-hand corner. The visor famously was tethered to about 3 cords for power and for graphics display, and it was quite heavy, and it was quite common to actually pull the plugs out of the wall and everything else. They also required what was called lighthouses, which were the sensors were external facing in to map your movements, and that's how you got your place in VR, as opposed to the Quest 2, which maps you from the inside out, maps your environment from the inside. The device can be tethered to a computer. It's generally designed to be Wi-Fi and wireless. So the same as the HoloLens, you can run the application directly from the Oculus, which requires you to actually compile the software and load it on. Sorry, not the Oculus, the Quest 2. So you can load it onto the actual device. You can run it through Wi-Fi via a computer, but you need a beefy system and a good network, good Wi-Fi network, or you can do the old-fashioned tethering using a USB-C cable, which is a bit hit and miss and generally outdated now. This is the functionality in the latest versions of the Quest 2, where you can phase between reality and virtual reality. You can see on the left-hand side there, by sliding a scaling slider, you can see your keyboard in front of you, and that's a virtual representation of the keyboard overlaid a real keyboard. So the aim there is that you can actually do work using a real keyboard in virtual reality as well. And then on the other side, we can see a mixed reality function, such as a virtual light switch, which is used in the real room. And this can be used to kind of add in functionality to a very simple space, and it can be also used to gather metrics on things such as movements, like head angles or head gaze, like where the head is facing. And this unit only has a single light sensor on the inside to indicate whether someone is wearing it, and this is pretty much more for power usage. The device switches itself off after a while. There are no inward sensors, unlike the next unit I'll show you. So this unit does have an inward sensor as well as outward sensors. Outward sensors to capture the environment. The inward sensors capture facial recognition and face gestures, so you can smile and it will show you smiling or your equivalent smiling in reality. This is the general future for head-mounted devices. If we look at, this is the most recent headset from Meta, and it looks as though the trends will merge MR and VR together. So you'll be able to see the outside environment if you want, but you can also see a pure VR environment if you also are willing to flick the switch. Each device is going to be geared towards doing everything. And I think that every VR headset manufacturer is going towards this model as well. This is the Meta Quest Pro. It's priced for professional use. So the previous Quest was about 600 Aussie dollars. I think it's gone up a little bit more now. This Quest Pro has come in at about 2,500, if not more, Aussie dollars. So it's definitely designed for developers and for professionals to develop applications. The limitations of VR in general is that it's very hard to demonstrate. It's very much an individual experience, and you have to try it to really use it, to understand it, and to actually appreciate it. Is it a trend? It once was considered to be similar to 3D TVs, but Gartner, which is the technological research and consulting firm, and famously produced the Gartner hype cycle, originally predicted it will take 5 to 10 years to reach maturity about 2 years ago. And then this year they removed AR and VR completely from its hype cycle, and they considered that it was no longer an emerging technology. It's now ready to move from a pilot position into productivity in the enterprise space. Overall, XR as a commodity is considered to be worth about $87 billion US by 2030. And this is also been bolstered by the games industry and also the film industry. This is what the Meta Quest Pro looks at, and this is the advances made between the last version. You can see it's changed from black and white to color, and the pass-through is much cleaner and the resolution is better. This is generally touted as being a platform for the metaverse. The metaverse itself is worth mentioning. It's entering its hype cycle at the moment. Whether the metaverse occurs or even succeeds through Facebook remains to be seen. Facebook are hedging a lot of bets on making it a thing, and this is the hardware that they're going to do it with. It generally provides better color, better fidelity, and there are complaints about the peripheral vision and the weight of the unit, which everyone was expecting to be much lighter than every generation prior to it. So far, every headset has generally been lighter than the one before it. This one has been quite heavy. And there's a general criticism about the cartoonish nature of these human representations. Not everybody wants to be working a day job in a cartoon in the hybrid workspace. So this generally also showcases that the headset is capable of recognition there. You can smile, you can raise your eyebrows, wink, and it will pick up those gestures as well. So this diagram will show a very simplified workflow, of creating XR applications. Generally, the strategy and planning follows and mimics games production for computers. So you storyboard and use requirements very similar to how you would in the movie industry and what each scene is going to look like. And then you create the 3D assets, which is a specialty in itself. And because VR and AR typically use a lot of interaction, there is a strong emphasis on user experience and user interaction design as well as part of that creation of assets. XR development, which is probably the largest, need programming and coders to actually work within games engines and also on the web. There's an increasing amount of XR used through the web, either through a phone, but also generally it's going to be on devices as well. The games engine, a quick note about those. There are two big contenders. One is Unity, which is a Danish company now housed in San Francisco, and the other one is Unreal Engine. Both of them are big contenders for big business. Unity just bought Weta for $1 billion. Weta is the production house that makes special effects for Lord of the Rings. So they see this is the future of where the games engines are going to go into, is visual effects, but also in controlling industry as well. Testing is very important and takes a very long time, much longer than everybody anticipates. And eventually the application or the game at the end is deployed and tested for demonstration and also training. So how can we leverage this functionality for XR and for digital twins being used in designing a Cobotics system? So it provides us with a tool that we can use to run iterations of prototypes and interaction, which we can use a real robot in a real space as well, or a virtual space. So we can recreate these spaces, we can change them, adjust them, modify them, and then prototype different scenarios while interacting with the actual virtual Cobot. And then we can also mimic those simulations in testing with the real world. So in creating digital twins and experiencing them as prototypes of a shared human space, we can also monitor human movement and the cobotic actions as well. This project was the first of our research translation projects with our industry partner B&R Enclosures here in Queensland. And we chose a role in the factory production line that was strenuous and somewhat taxing as a starting point for creating a VR application that we can use as a future platform for research. And also we can implement in different areas of both B&R's factory processes and for other industry applications as well. These photos were taken inside the gasket application room of our industry partner B&R, and they show what could be called the main task, which is loading and unloading the panels of the gasket machine. So metal panel doors are put onto the machine, and a gasket is applied as a foam liquid, which then sets as a hard rubberized foam. So the method of qualitative research here is to do observations and ask plenty of questions. And the aim is to observe and then document and catalog the actions of that human, noticing his decisions. And then also start planning for a place where the Cobot can sit and work around his workflow. So if we use VR as a toolkit to design the Cobot placement and actions, we can also use it to monitor and understand how it will alter how he works. And then here we were creating a first stage of the digital twin, which is technically a prototype of this workspace and then we can use that to simulate and eventually predict the best opportunities for the human to share this space with a cobot. So this is the task itself, which is loading the panels on. This is a very, very quick job. When it starts, the panels are loaded on and there's little downtime between from one panel to the next. The gasket machine needs to run constantly to be efficient and to not waste material. And the second part of this task is to load and stack the gaskets so that they can cure effectively. This is a climate controlled room, so the gaskets will sit and cure and reach full curation at about 24 hours as well. Quite a strenuous job. It's mentally taxing as well. In between, there's a lot of decision making during the actual task, but also monitoring of equipment, checking the gasket machine, and micro adjustments. And we likened it to kind of being a curator in the zoo, looking after a big animal. The gasket machine is seen there behind the cage. And Dave, who's the operator here, has to constantly monitor how the gaskets are being poured and whether they're being applied properly. It seems straightforward, but there's plenty of subtle, small tasks that have to be performed as well for this to be an acceptable gasket, both as part of the production and also as maintenance in the gasket machine. So the challenge here was to capture the space as well without interfering with the production and getting in the way. I had a look at some of the scanning devices, and all of them require generally a tripod and an old-fashioned scanner. A couple of years ago, iPhone, the new generations, released a phone which has a LiDAR scanner on the back. If you have a new phone, it's a little black circle in the bottom corner of the cluster of camera lenses. And the LiDAR scanner is able to capture depth and also can create point clouds, which you can see in the right-hand image there. This is 3 different applications from the iPhone. 3D scanner app, which is a free one, which allows you to export your models out of the phone without charging you. Scannerverse is the same. There you can see the difference on the left-hand side. We have LiDAR. No, we don't. Sorry, we have photogrammetry. So it's using the photos and the LiDAR to actually create a 3D model. In the middle, we're using predominantly LiDAR, using Scannerverse. The red and white areas are areas that are fuzzy and haven't been captured yet. And then in Sitescape, which is a paid application, it's producing a point cloud as well. Old scanners were typically about $80,000 to $100,000. They could scan very long distances, 100 meters or so. A mobile phone is limited to about 6 meters, but in terms of ease of use of getting in and out of that space and around the workers, it's an impressive piece of technology. And these are further functionalities and processing which happens on the actual phone itself. We can capture the room and raw data such as the walls and windows. It will pick up items such as desks and chairs, and then we can create a very quick mock-up of that space. You can see in the second to left gray image there, the gasket room one, a rough geometry of the space, and then we can use that along with the other scans to kind of start placing items in that room when we create an asset for the games engine to use. Processing typically is between 1 minute and 6 minutes, depending on the fidelity and the resolution of the scan that you want. The scans typically look like this. I tried scanning this room, which was about 11 by 8 meters in one sitting. The phone overheated, got very hot and started to lose data. So there's definitely a cap on the amount of geometry I can take into the phone at any time. You'll notice here that the scan has done a realistically good job. I was scanning a lot of cages, which has got holes in it, so empty space, and it's actually managed to capture elements of the cage. This using a combination of a point cloud and also this photogrammetry and LiDAR, I could actually create a decent model. And this was the end result, is to basically start creating assets. This is work in progress. There's no textures on this. This is viewed within Unity. And we're starting to create those elements of the space where we'll be able to see in VR and walk around that space and avoid and interact with certain elements of it. So the current work in progress, this is the most recent video that we've captured. It's square because it's been captured on one eye of a VR headset. Is to how can we place a robot within this room? We've had an initial challenge in that the ideal space for a smaller robot would be to be placed in that area where the human typically needs to walk between. So a challenge would be how would we place this robot or a bigger robot within this space without it getting and being able to share this space with the human itself. You can see here that we're doing a very simple pick up and place onto the gasket, and then pick it up from the gasket once it's been pumped the gasket machine, and place it back down and palletize it and stack it on the other side on what would be a pallet. Very rough, but it's taken a while for us to get these movements working quite fluidly. The future for this VR platform is where we want to take it into mixed reality, so we can attach virtual robots into real world objects. We want to make a connection to a robot, which we're mostly succeeded at doing so far, and to visualize XR actions over the real robots in real space and be able to control that movement in AR and see it represented and mimicked in the real robot. We want to use multiple users in VR and XR. We have a student project coming up, which we're hoping to map other spaces within BNR. And ultimately, we want to use the platform to integrate and then test a Cobot in a real working environment. So a real Cobot in a real working environment. And generally, we're hoping also that immediately we can work with our colleagues in the other programs, particularly looking at machine learning to optimize the placement of robots in this space. And that's the end of the presentation. Thank you.
Bravo. Thanks so much, Al. I think we've run out of time.
But we have, yes, sorry.
Excellent overview. But everyone, please save your questions for the launch, because you'll have opportunity to see this in more detail, and we can have more discussions at the launch.
Definitely, you'll be able to see a demonstration of the actual VR app, and hopefully we'll be able to see the robot working as well with it. So please come along to the launch. And if you have any questions, please look me up on LinkedIn or find my email. I'm on Google. I don't try to hide myself. Thank you. Thanks for coming today.
Thanks, Al. Interesting.
Thank you.
Thanks, Al.
Thanks.
Thanks, everyone. Thanks, Al.
Thank you. Bye, everyone.
Yeah.
Thank you.
Thanks, guys. Great.
Great. Thanks, Chris.